Welcome to this lecture. In the previous lecture, we looked at example 55, where we made use of the Excel add-in solver to solve a two-dimensional LP problem. In this lecture, we are now going to look at a similar example, but with more than two decision variables. So we are going to look at a higher order LP problem. So example 56 is a follow-up of example 55, but you will see that now we have more than two decision variables. A filling station needs to order petrol, diesel, and unleaded petrol to sell to their clients. The cost of 1 ton of petrol is 8,000 rands, the cost of 1 ton of diesel 9,000 rands, and the cost of 1 ton of unleaded petrol is 8,500 rands. The net profit from selling a ton of petrol is 1,600. The profit for diesel is 2,000 rands, and the net profit for selling a ton of unleaded is 2,100 rands. The total funds available is 100,000 rands. Due to storage restrictions, the garage cannot purchase more than 8 tons of petrol, 8 tons of diesel, and not more than 5 tons of unleaded petrol. So the question is now, how much petrol, how much diesel, and how much unleaded petrol should be purchased to receive the maximum net profit? So when we get an example like this, we would first like to formulate this question into an LP model. Now, if you go back to example 54, where we looked at how to formulate an LP problem, you will remember that we first need to identify the decision variables, then we set up the restrictions, and then we find the objective function. So if we look at the decision variables in this case, we can then define them as follow. Let X1 denote the quantity of petrol that the garage will purchase. X2, the quantity in tons of diesel that the garage will purchase. And X3, the quantity of unleaded petrol that the garage will purchase. So that is my three decision variables. And then we have certain restrictions. So again, very similar to examples 54 and 55. My restriction is that a ton of petrol costs 8,000 rands, 9,000 rands for the diesel, 8,500 rands for the unleaded petrol, and we have available only 100,000 rands. So that will make out my first restriction. Then my storage space, I have available only storage space for only 8 tons of petrol. That will be my second restriction. Then 8 tons of diesel, so that will be my third restriction. And then we have storage space for, what color will I use now? Let's make it white. Then we have storage space for only 5 tons of unleaded petrol, and that will be my fourth restriction. So we can summarize our LP model in the following way. My constraints are the following. This is the price, the available funds. This is the storage space for petrol, for diesel, and for unleaded petrol. This last restriction is the non-negativity restriction. And then, of course, we also have to have an objective function. So if we go back to our question, the net profit from selling a ton of petrol is 1,600, for diesel 2,000, and for unleaded petrol 2,100 rands, and we would like to maximize our profit. So that will then be translated into the following. We want to maximize the objective function, which is given by that mathematical model. If you are uncertain how this LP problem is set up, I refer you back to a previous lecture where we looked at example 54, where we formulated an LP problem. So for an LP problem in a two-dimensional space, we looked at the graphical method to find the solutions for our two decision variables. In this case, we now have three decision variables, x1, x2, and x3, and it becomes very hard to solve this graphically. So we will not solve this by hand. We will make use of the solver add-in in Excel to solve this LP problem. Now, the procedure we're going to use in this lecture is very similar to what we did in a previous lecture where we looked at example 55, and that was where we solved a two-dimensional LP problem, example 54, that was formulated in example 54. So I'm going to look at how to solve this three-dimensional problem in Solver, but it works exactly the same as what we've done in a previous lecture. Okay, what I have here is my Excel sheet. I have three decision variables, x1, x2, and x3. I set my three decision variables, the initial values for these three decision variables, I set them all equal to 1. And then in line 2, I specify my objective function. So that's the profit, 1,600 rands for each ton of petrol, 2,000 for each ton of diesel, and 2,100 for unleaded petrol. And in column E, I put in the formula similar to what we did previously in example 55. So there you can also see the formula that I have in column E. Then in the third row, I have my first restriction, and that's the cost for petrol, diesel, and unleaded petrol. And there you have the formula. So that will be the cost if I start out with 1 ton of petrol, 1 ton of diesel, and 1 ton of unleaded petrol. And then in the last three, I have my restriction 2, 3, and 4. Okay, and now we're going to make use of Solver. So we go to our Data tab, and there you should find your Solver. If you haven't added this add-in Solver, I refer you back to a previous lecture where I showed you how to upload the Solver add-in. So for now, I assume that you already have that add-in. So I click on Solver. First of all, I want to set my objective. My objective is the value of my objective function. So that would be in cell E2. I would like to maximize my objective function. So in this case, I would like to maximize by changing the variable cells. Now the variable cells are the values for my decision variables, so it will be those three there. And then I want to add my restrictions. So I click on add. My price or the cost must be, remember this is a drop-down menu, but we want it to be less than or equal to 100,000 rands. Then the storage space for petrol must be less than or equal to 8 tons. The storage space for diesel must be less than or equal to 8 tons. And then the storage space for unleaded petrol is a maximum of 5 tons. If you have typed in your last restriction, you click on OK. Then remember that this box must be ticked. Make unconstrained variables non-negative. That is to have the non-negativity restriction. And then the solving method that we are using here is the simplex LP for linear programming. And then you can click on solve. And you will immediately see that the values for x1, x1, x2, and x3 now have their optimum values. But we can also click on reports, answer, and that will give us a more complete report on the results. So that's in a separate sheet. So if I click on answer report 1, you get this sheet with the results. So here you can see that the original value for my profit, for my objective function, where if by setting the original values for x1, x2, and x3 equal to 1, the original value for my objective function was 5,700 rands, and then the final value, the optimal value, the maximum value for my profit is 23,277 rands. Then in the next table, I have my 3 decision variables, x1, x2, and x3. The original values, we have started by setting them all equal to 1. And then we have the final values. So the final values give us the optimal values to maximize our objective function or our profit. So for x1, we have a 0. So to optimize our profit, we have to buy no petrol, 6,39 tons of diesel, and 5 tons of unleaded petrol. And if we go down here, you see a table with the constraints. So we have 4 constraints. The first one is the price constraint. In the column formula, you will see that that column gives you the upper limits of your constraints. So the price was set at 100,000 rands. Then we have the storage space for petrol, diesel, and unleaded petrol. So the storage space for petrol was 8 tons, for diesel 8 tons, and for unleaded petrol 5 tons. Then in the column cell values, it indicates how much of these resources are actually being used in our optimal solution. Now we have 100,000 rands available, and we have used 100,000 rands in the optimal solution. And therefore we say that this constraint is binding. Binding means that the optimal solution uses the most extreme possible value of the restriction. If you go to the second restriction, the storage space for petrol, we have 8 tons of storage space available for petrol. In the optimal solution, we will buy no petrol, and therefore this constraint is non-binding. Non-binding means that the optimal value does not reach the limit of the corresponding restriction. The limit is less than or equal to 8, so the upper limit is 8 tons, and we are not using any of that, therefore this restriction is non-binding. Then for diesel, the restriction is 8 tons of storage space available. In the final solution, we will use 6,39 tons of that storage space, and therefore it is non-binding, and the slack gives me the difference between the actual storage space used and the storage space available. And then lastly, the fourth restriction, we have 5 tons of storage space available for unleaded petrol. We use 5 tons of storage space, so we use the full capacity. Therefore, this restriction is binding, and therefore the slack is equal to 0.